Hi everyone, this is 2.6 Notes, Algebraic Proofs. In our last section we looked at postulates about points, lines, and planes, and as I mentioned in the last section, we're not writing paragraph proofs at all. We're going to totally focus on two-column proofs. And in this section we're going to get our feet wet a little bit and do that solving algebraic equations, just to get used to this two-column recording method. Okay, so what is an algebraic proof? An algebraic proof is solving some kind of algebra problems, or usually, let's say, solve an equation for a particular unknown. And the main thing here on the proof side of things is that we're going to justify every single step that we make. And we're going to usually justify that with properties of real numbers, generally properties of equality. I'm abbreviating here. Okay, so let's talk about those properties of equality. So all of these here that I have listed in this table, we're going to be going through each one. They're, in general, properties of equality, and that's what we use in order to execute our inverse operations. So when we're solving an equation, we undo the arithmetic operations that are around that unknown. And what allows us to undo those is properties of equality. So let's take a look at each one. First one, addition property of equality. The addition property of equality says that we can add something to both sides of an equal sign and still maintain equality. So if A equals B, then we can add something to both sides, and I'm going to say A plus C. I can add C to both sides. Equals B plus C. I can add that same quantity to both sides of the equal sign and still maintain equality. Likewise, subtraction. I'm not going to keep writing the ifs and thens. So A equals B, then A minus C equals B minus C. I could subtract the same quantity from each side. Likewise, multiplication property of equality. A equals B. I can multiply both sides by the same quantity. A times C equals B times C, and still maintain equality. A equals B. I can divide both sides by the same quantity. A divided by C is going to equal B divided by C. All of these things we do by second nature when we solve equations. We just don't think about it in this level of detail. Okay, distributive property of equality. That means that if we're multiplying some particular sum or even difference by a number, for example, let's say A times the sum of B and C, well, I can distribute that A across each of the numbers in that sum, and that would be equal to A times B plus A times C. That's the distributive property. By the way, the distributive property, as we've talked about in class, is what allows us to combine like terms. So we can also use that as justification to combine like terms. Okay, I'm sorry, we have a little bit of I had a typo here. This is reflexive. Reflexive with an X. Reflexive property of equality. The reflexive property of equality, think of your reflection. Okay, if you're looking at yourself in a mirror, you see yourself. So all this means is that something equals itself. And this may seem like a very small detail, but we're actually going to use reflexive property quite a bit in this course, so it's important to get comfortable with it. Next, symmetric property of equality. So think of symmetry, and if we have if A equals B, then look at that in a symmetrical point of view, then B equals A. That's kind of a symmetry. Transitive property of equality. Think about the root word trans. Trans actually means across or through. So if you think of transcontinental railroad, that would mean that that railroad goes across the continent. Or transport, you're moving something, goods, across a particular distance. So transitive property of equality, we're actually transferring value across three different things. For example, if A equals B and B equals C, well, then you can see that A must equal C if they're all equal. So we would finish that up to say that A equals C. We're almost transferring that value of A over to C across three entities. We're going to be using this property quite a bit. Now, transitive property of equality, to me, is rooted in substitution property of equality. So if you think of this in terms of a Venn diagram, there's pure substitution, and transitive property of equality is sort of a complete subset of substitution, whereas not all substitution is transitive. So think of it that way. Okay, so substitution property of equality, that would just mean, for example, that we have some kind of expression, so A equals B, and I tell you that B equals 5 or something. Well, I can substitute that in for B. And this type of thing we do all the time when we evaluate expressions. So if I said evaluate, I'm just making things up here, 2x plus 1 when x equals 4. Well, you would take that 4 and you would just substitute it in there, and you would say that 2 times 4 is 8 plus 1, and this is the process of basically evaluating an expression. First substitute and then simplify. So this property here above, transitive, going back to my original comment, if we're substituting here in C for B, you can easily see that A equals C. So transitive property of equality, it's kind of this transfer of value across three entities, but it's definitely rooted in the substitution property of equality. So example number 1, we're looking at solving an algebraic equation, and we do that all the time, and we've been doing that for a long, for several years now, but we might not think about every step that we do. So the idea of doing algebraic proofs is to get used to formalizing our thought process and formalizing and becoming proficient at setting up two columns using statements and justification. So when we do these two column proofs, and that's what this is, we've got two columns already set up for us, we're always going to have this first column being our statements. This says algebraic steps, but in general we're always going to make that first column statements and the second column are reasons or justification. Alright, so let's take a look at this example here. We've got solve this particular equation. So the very first thing we do is write down what has been given to us. So this equation here is just repeated right here in the first row. So very first row is always going to be the given, and our justification is that it's been given to us. Now, in this particular proof, normally everything will be blank. So you will set up a table, you'll have your statements, you'll have your reasons, and then you'll work your way through it. But here, just to kind of get used to it, all of the statements have been set up for us. So what's happened here between 1 and row 2? What's happened? Hopefully you can see that what's happened is the distributive property has been applied to eliminate those parentheses. So we would just simply list that as a reason, distributive property. And it's really the distributive property of equality, but I'm okay if you just write distributive property. All right, row 3. What's happened here between 2 and 3? Hopefully you can see that we've combined like terms. We've combined the constants. 10 minus 28 is negative 18, and we've also combined the 6a and 4a. So you can see that we've combined like terms. Now combining like terms is definitely rooted in the distributive property, but I'm okay if you just use what's natural, combine like terms, because that's what's really happening here. Now what's happened between row 3 and row 4? It appears that we are adding 18 to both sides of the equal sign. And we're doing that as we would normally do. We go to the unknown, we look what's around it, and we undo those operations from the bottom of PEMDAS up. So we kind of are undoing all the operations around that unknown in the opposite direction of order of operations. And so we would naturally add 18 to both sides is really what's happening here. Well, that's the addition property of equality. That says we can add the same quantity to each side of the equal sign and still maintain equality. And then we simplified here. We've combined negative 18 and its opposite, positive 18. And we combine 92 and 18 on each side, and that's combining like terms. Now, if you said simplify, I don't know, I think I'd rather have you combine like terms as a reason. But I probably would be okay with simplifying. Negative 10a divided by negative 10 and 110 divided by negative 10. What's happening here? We're moving up the ladder here, and now we're undoing this multiplication between negative 10 and a with division. So this is division property of equality. I'm abbreviating here. And finally, what did we do? We took 110 divided by negative 10, and we basically just simplified. And that is our very first algebraic proof. Okay, let's move on to another example. Science. If the distance d of an object travels is given by the equation d equals 20t plus 5, the time t that the object travels is given by t equals d minus 5 divided by 20. Write a two-column proof to verify this conjecture. Okay, so the very first information we've been given is this equation right here. D equals 20 times t plus 5. And so we would restate that in the first row. We always restate the given in the first row, or multiple rows actually. You could be given a lot of information, and the justification is that that's been given. And the very last row is going to be what you're trying to prove. So that's always going to be, what you're trying to prove is always going to be the bottom of that proof. Okay, again, we're just trying to get used to this new technique of proving what we're doing. And so I've got everything provided for us, although we're going to need to get to the point where we can do this completely blank, make our own table, and justify each step. So we have an equation, and we're trying basically, as you see in the what we're trying to prove is we're trying to isolate t. We're trying to solve for t in terms of d. So how would we rearrange this equation? Well, same way we would solve any equation. We go to the unknown we're trying to isolate. We undo the operations around it using inverse operations. Okay, so the very first thing, and of course we'd always do that in the reverse order of operations. So we'd go from the bottom up. So what's around that t? We've got multiplication and we've got addition. So we want to undo that addition first. And we would do that by subtracting 5 from both sides. And so that's what's happening here on number 2, and it's already been simplified for us. So that subtraction has happened and it's been simplified. So we would say subtraction property of equality. And also it has been simplified for us, so everything's been done at once. And a lot of times you may do that in your own work. You may do a lot of mental math and sort of combine multiple steps. Okay, so what's happening between row 2 and row 3? So we've got row 2 here. It appears that we are continuing to isolate t, undoing that multiplication of 20 with division. So we've got the division property of equality. And it's also been simplified. You can write that or not. I'm okay with just division property of equality. And now take a look at what we have here. We have this algebraic expression on the left and t on the right. And the only thing that's changed between 3 and 4 is that we've spun them around. We have t on the left now and that algebraic expression on the right. And one of the properties that I introduced in the beginning is called the symmetric property of equality. So that's what's happening here. Remember that that property says if A equals B, then B equals A. It's just kind of symmetry, and so that's all we're doing there is solving for t. Okay, very good. Let's move on. Example 3. If the formula for the area of a trapezoid is A equals 1/2 times the height times the sum of the two bases, then the height h of the trapezoid is given by h equals twice the area divided by the sum of those bases. Prove this conjecture. Okay, so we're always going to start out with the given, and we're going to write that in row 1. And the reason we would provide is it's been given to us. And we are trying to basically rearrange this formula for the trapezoid and solve for the height. That's basically what we're trying to do. And the conclusion of this if-then statement is always going to be what you're trying to prove, and it's going to be the last statement in our table. Okay, so this time we're given the reason, multiplication property of equality, and we're trying to solve for h. We're trying to isolate h. So reverse order of operations. What's around our unknown that we're trying to solve for? We're trying to rearrange this equation in terms of the other variables. Well, h is being multiplied by 1/2, and it's being multiplied by the sum of the two bases of the trapezoid. So what could we do to basically undo this division? Multiplying by 1/2 is really h being divided by 2. So how can we undo that division? Well, we can multiply both sides by 2. So let's say 2a equals 2 over 1 times 1/2 times the sum of the bases times h. So we've multiplied both sides by 2. And now we have some simplification that we could do all in one step. So 2 over 1 times 1/2, that would be 2 over 2 or just 1, so that would cancel. Now h is being multiplied by the sum of these bases. How can we undo this multiplication? We would undo that multiplication with division. So we're going to basically divide both sides by this sum, b1 plus b2. Whatever I do on one side of the equal sign, I have to do exactly the same thing on the other to maintain equality. So you can see here that we have the division property of equality at work. We're dividing both sides by the sum of the bases. And then we're simplifying. So when we do that, you can see that those that sum here would also cancel, and we just end up with 2 times the area divided by the sum of the bases. And finally, all we're doing is putting the height on the left where it used to be on the right, and just like the previous problem, that would be the symmetric property of equality. We're just rearranging the furniture there so that we're solving for the height. Alright, example number 4. If angle A is congruent to angle B, and the measure of angle B is twice that of the measure of angle C, and the measure of angle C equals 45 degrees, then the measure of angle A must be 90 degrees. Write a 2-column proof to prove this conjecture. As always, we take the given, that's the hypothesis, and that would be the first thing that you would write in your 2-column proof. So angle A is congruent to angle B, measure of B is twice angle C, and the measure of angle C is 45 degrees. The degrees looks like it's been dropped off here, and all of that is given to us, so we would write given. Now, the measure of angle A equals the measure of angle B. This is sort of what I would call a nitpick, and I'm not going to hold you to this kind of level of detail throughout the course, but I do want to make the point that if 2 angles are congruent, then their measures are equal. Remember, in the beginning we said that the word congruent, the actual definition of congruent, stands for equal measure, and that is whether we're talking about segments or angles, or eventually we're going to be talking about triangles and other polygons being congruent. So congruent, direct translation, is equal measure. And that's all we're saying here. If those angles are congruent, then the measure in degrees must be equal. And so the reason we would give for that is that's just the definition of congruency, that their measures are equal. And I am going to abbreviate because it's small. Definition of, and I'm sorry, my writing is very messy here. Definition of congruency. Okay, so this time on row 3, we're given the reason, and we have to figure out what the statement must be. So my advice to you is look to see what's happening in 2, what's happening between 2 and row 4, to see, you know, what could possibly go in 3. And we're given as a reason transitive property of equality. And just to give you a memory jogger, that means we're transferring this value. If A equals B and B equals C, then A must equal C. So we're kind of transferring this value across 3 entities. And you can see here that measure of A equals measure of B, and we're told that measure of B equals twice that of measure of C. So we're going to transfer across these 3 entities. And what that looks like here is measure of A. So we would say the measure of A equals the measure of B, and the measure of B, whoops, I don't like the way that looks, measure of angle B equals twice the measure of angle C. So we're kind of transferring these together here. So we would say that the measure of angle A must equal 2 times the measure of angle C. And that's the transitive property of equality at work. Now how do we go from this measure of angle A, nothing's changed here on the left side of the equal sign, to 2 times, instead of the measure angle C, we put in 45. Well, that is pure substitution. We substituted the value that we were given for the measure of angle C. We were told it was 45, and we substituted. And then we simplified. 2 times 45 is 90. So that's all we did on the last step, simplified. And so we've reached our conclusion that the measure of angle A must be a right angle of 90 degrees. Okay, example 5. If segment AB is congruent to segment CD, and segment CD is congruent to segment RS, we should actually have segment lines here, and AB equals 12, then RS must equal 12. Complete a two-column proof to prove this. So we would take all of the given information that we have here, and we would put that right up here on the top. So AB is congruent to CD, CD is congruent to RS, that's been given to us. AB is congruent to RS. So this is a classic example here. A equals B and B equals C, therefore A equals C. So that's all we're doing. We're kind of transferring this value across 3 entities, and we call that the transitive property of equality. Okay, the next line, we don't know what the statement is, but we've been provided the reason is definition of congruent segments. This is where we have 2 segments that are congruent, therefore their measures are equal. So it may seem like a minor point, but we're basically saying the length of AB is equal to RS because their segments are congruent. Now how do we go from AB equal to RS to AB equal to 12? Well, we were told right up here that AB equals 12. Okay, so don't overthink it. That was part of the given. Okay, so even though we didn't write that up at the top, that's still part of the given. Okay, so AB equals 12. We are going to substitute here 12 in for AB. So 12 equals RS. So I'm basically taking 3 and I'm substituting in 12 for AB. And that's just pure substitution. I'm going to add another row here, 4A. That's substitution. And then finally, how come we can say if 12 equals RS, then RS equals 12? We're just flipping around quantities on either side of the equal sign, and that's the symmetric property of equality. Okay, that ends the video. Hope this helps.